Okay, in this video we're going to take a look at a very interesting property of waves, and that is what happens to waves when they interact with each other. And that process is called superposition. And the idea is that when two waves pass through each other, they meet each other, ultimately what ends up happening is they each act independently on the medium, so they cause the medium to be displaced or disturbed, and their disturbances will add up. That is to say that the superposition of waves is simply adding the displacement of two waves that meet at a particular point in space. Now, this could be really complicated. I mean, we could really make this very complicated if we really try and think about periodic waves. So because periodic waves are a little difficult to visualize and kind of hard to draw on a piece of flat paper, we're going to mostly focus on pulses. We're going to look at single pulses. We're going to send a pulse from the left and a pulse from the right. We're going to let the two meet, and we're going to look to see what happens when we add the displacements of those two waves. Now, when they meet, they can meet in such a way that they will constructively interfere with each other or superpose with each other, meaning that their displacements will be added, or it could be that they destructively superpose with each other, so that one wave is going in one direction while one is being displaced in the other direction, and they will partially or completely cancel each other out. So let's take a look at several examples of this. It'll be easier for you to understand superposition of waves if we just simply look at some examples. I'm going to very carefully draw this picture. I'm going to draw a rectangular pulse, which is, it's a little strange. It's going to be very difficult for me to produce a rectangular pulse on a string or something like that. But let's assume that we can create a pulse which has a height of 1 and a width of 2. Now, it doesn't matter what the units are. It could be 1 centimeter or 2 centimeters or 1 meter and 2 meters. It doesn't really make a difference. But what I want is a pulse which is twice as wide as it is tall. And then over on the other side, this wave is going to be traveling towards the right. On the other side, we're going to have a wave traveling in the opposite direction. It has a slightly different shape, so it's going to be a triangular shape, but it is also going to have the same height of 1, and it is going to have the same width of 2. Okay, so for the purposes of looking at superposition, we're always going to look at waves that have a width of 2. Okay, now what the shape of the wave is, or what the height of the wave is, that will vary, but the width of the waves will always be 2. So just for this first example, I'm going to show the waves meet. I'm going to show what the superposition of the waves looks like when they meet, and then we're going to let the waves continue to pass by and move on, and only for this first one will I draw what it looks like after the waves pass through each other. So essentially, when the two waves combine together, they will be perfectly on top of each other. That means that they will have a width of 2, just like both waves have a width of 2. So when I put those two waves on top of each other, they will lay perfectly on top of each other. And the question is, what does the new combination of those waves look like? So in this case, all I'm going to do is, I'm going to think about the two waves. I'm going to think about taking this wave and placing it in the same location where this wave is at, and I'm going to add their displacements. So if you notice, the left side of this wave, when I move it over here, it will line up with the left side of the rectangular wave. When I match up the right side of the triangular wave on top of this wave, it'll match up with the right side of this wave. The middle of this wave will match up perfectly with the middle of this wave. So all I'm going to do is I'm just going to simply add their displacements, and I'm going to kind of put a few points on this to show me where would those displacements put me. So if I look at the left side, I can say I have a displacement of 1. If I look at the left side of this one, there's no displacement here. It does have a displacement of 1 in the middle, but at the edge, it has a displacement of 0. So 1 plus 0 is 1. And if I look at the right side, I see I have 1 plus 0. That is also going to be 1. But what happens when I add the middle together? So here I have a displacement of 1, and here I also have a displacement of 1. So I'm going to go 1, 2, and that's enough for me now to visualize what the shape of these two waves are going to look like when they meet each other. They are going to meet each other and look something like a little house in this particular example. So at every point, I have simply added the displacement of this wave to the part that it matches up with, and I've taken the point that I'm looking at to be when they perfectly line up with each other. Now, as they first start to meet, they'll have like a little more complicated shape. But once they get completely superposed on top of each other, then they will have this shape. And these two guys are going to have the same speed because they're traveling on the same medium. And so at this point, we have wave A and wave B. Wave A is still continuing to travel in this direction, and wave B is still continuing to travel in this direction. So what's going to happen after they pass? They essentially, when they reach this point, the wave suddenly gets really big. It gets a height of 2 here in the middle, and still has a width of 2. Well, what's going to happen is the waves will then pass right through each other, and they will go on about their business as though nothing ever happened, as though they did not even notice that the other wave was there. Okay, now the thing that does notice that the waves are there is the medium. Okay, and in this case, the medium that we're looking at is a string. So the B wave continues to travel through, the A wave continues to travel off in its direction, and the two go about their business as though nothing ever happened. So they are not destroyed, they don't bounce off of each other. Waves do not interact in that way. They simply cause the displacement of the medium to be a combination of the two waves. Let's take a look at another example. We'll take a look at several examples. I'm going to do one more where I'm going to show you, and then I'm going to make 2 examples where I'm going to ask you to pause the video and predict what you think the waves will look like when they superpose. Let's keep the same wave on the left side. So 1 high and 2 wide. All right, now let's look at the wave on the other side. Let's use that same wave that we were traveling with before, but let's flip it upside down. So we're going to send a pulse on this side, but this time it's going to be triangular in shape, but on the opposite side. So the B wave, still traveling in this direction. It still has a height of 1 and still has a width of 2, just like the previous one. Okay, so when I superpose these 2 waves, they will meet, they will have a width of 2, and the question is what shape are they going to make? So if you go look again, the left side of this wave has no displacement and the right side has no displacement. So nothing has really changed from the previous situation. We're going to add 1 to 0, and that's going to give it a displacement of 1. But look what happens in the middle. I have a displacement of +1 here, but here I have a displacement of -1. And 1 plus -1 here in the middle gives me a displacement of 0. So that means that the combination of these 2 waves must look something like this. And I imagine that if you just think about taking this wave and going over and adjusting the displacement of this wave to take into account this one, you'll see that it's going to press down this middle portion and it's going to give us this kind of M shape. It still has a width of 2. In this case, it still has a width of 1 on the edges, but in the center, it actually has no displacement. And again, what's going to happen to 2 waves is the triangular wave is going to continue moving off in this direction, while the rectangular wave continues to move off in this direction. So let me give you 2 examples. I'm going to still use triangles, but I'm going to use slightly different shaped triangles, and I'm going to ask you to pause the video as I finish them so that you can test them out for yourself, and then I'll show you what the answers will look like. So for example number 3, we're going to stick with that same rectangular wave, 1 high, 2 wide. But this time the triangle on the other side, we're going to make it a little asymmetric so that it's off in one direction. Okay, this wave is also 1 high. It still has a width of 2. This guy still has a width of 2. Still has a height of 1. A is traveling in this direction. B is traveling in this direction at the same speed, and they travel the same speed because they're on the same medium. It turns out that the shape of the pulse doesn't have anything to do with how fast it travels. What determines how fast it travels is the medium on which you travel. In this case, it's a string, and so that's going to be determined by the tension in the string, and then also the thickness and the density of the string will play a role in how fast the wave travels. But it doesn't matter what the shape of the wave is. These 2 shapes are traveling at the same speed, and they will meet in the middle. And what I'm looking for you to fill in right now is this gap that I'm leaving. So I've left a gap that was too wide, and what I want to know is what will the shape of the wave be when these 2 waves combine together. So while you work on that one, I'll set up the next example. In the next example, I'm going to use the same rectangular wave, but this time we're going to flip this guy in 2 directions. I'm going to flip him upside down. I'm also going to turn him backwards compared to that first wave. So this guy still has a displacement of 1, but this time it's negative 1, and he still has a width of 2. This guy has a width of 2 and a height of 1. A is traveling to the right, B is traveling to the left. And what I would like to see is what will it look like here in the middle when these two waves meet each other. So at this point right now, what I would ask you to do is to pause the video, fill in both of these, and then if your answer turns out to be wrong, then you're just simply going to put an X through it. Don't erase it, because you want to remind yourself of the mistakes that you've made in the past so you don't make those mistakes again. And then you'll just redraw the correct answer underneath it. So you might want to leave a little bit of space under here just in case you need to redraw this one. And you can pause the video now. Okay, so we do the same process that we did before, which is I'm going to add the left side of this wave to the left side of this wave, and that is going to give me a height of 1. I'm going to add the right side of this wave to the right side of this wave, so that's 1 plus another 1 is 2. And just think about what's going to happen in the middle. Well, here, if this was 0 and this was 1, then this must be 1/2. So now I have 1 plus 1/2 in the middle. That must be a point about there, and the shape of this wave is going to look like this. And I think you could almost imagine that if I took this wave and I just stacked it on top of this wave, that's exactly what the shape that you would expect the wave to take on. It will have a height of 1 on the left, it'll have a height of 2 on the right, and of course it's still too wide, as all of the waves that we've looked at have been. Okay, so what's the effect of flipping the wave upside down and turning it backwards also? I'm going to do the same thing I did before. I'm going to add the left side of the wave, which is 1, to the left side of this wave. That's negative 1 plus 1, which is 0. I'm going to add the right side, which is 1 plus 0. That gives me 1. And if I add 1, positive 1 in the middle, to negative 1/2, I'll end up with 1/2. So I'll end up with something that looks like this. If you could see these two waves traveling towards each other, and you could freeze it right at the moment where they were on top of each other, where they were at the same point in space at the same time, you would see that this is what the shape of the wave is going to look like. Okay, I would really like to look at just one last example. We've been looking a lot at constructive interference. Here's a case of constructive interference. They're making the wave much larger than the original waves. We're looking at places where we have partial destructive interference. So the combination of the two waves is about the same size as this one, but smaller than the original wave on the left-hand side. Let's look at what it looks like when you have destructive interference, complete destructive interference. And the way that I would do that is I need to create two identical pulses, but I need them to be oriented in the opposite direction. So still a height of 1, still a width of 2. That's my wave A. And my wave B will be exactly identical to it, except that it will be on the bottom. It'll have a displacement of negative 1 and still a width of 2. So what are these two waves going to look like when the two waves meet each other? Well, these two waves, I'm going to have the opposite displacement in every single instance. So I'm always going to have 1 and negative 1, 1 and negative 1, in the middle positive 1 plus negative 1. So the result of those two waves would be, and while it might seem hard to believe, there will be just an instant. If you could take a picture of these two waves as they traveled towards each other, you would see that there was one instance in which they appeared to not exist anymore. The two waves appear. This wave is pushing up and exerting a force upward on the medium, while this guy is putting a force, and since the two forces are pointing in the opposite direction, they cancel, at least while the two waves are in the same position. Now, again, remember, they don't bounce off each other. They don't destroy each other. They just pass right through each other. They pass right through each other. And so the two waves will reemerge. They'll come back out, and the wave on the B wave, the B wave will now be on the left-hand side, continuing to travel away, and the A wave will be over on the other side. So the waves will not be destroyed, but temporarily, while the two waves were at the same position at the same time, they did actually have produced no displacement. So it would have appeared as though there was no wave. There was no wave on the thing at all. Now in the next video is what we're going to take a look at is we'll look at the same topic, superposition, but we'll look at it a little bit more deeply to try and think about what conditions could we get with periodic waves? Because remember, these are pulses. We're only looking at pulses. We're just looking at the idea of adding their displacements. But what happens when you have a periodic wave? How can you determine when you're going to have constructive and when you'll have destructive interference?